So we are entering the last module of the class, and arguably, if you want to get on the hype train, this might be the most exciting part of the course, which is mostly about reinforcement learning with human feedback. I cannot think of a better person to give this part of the module because just this semester, Gokul actually put out a very exciting paper, which in my view, has one of the clearest understanding of what's going on in what RL is doing for a lot of the language or preference fine-tuning. So take it away.
Yeah, thanks, Stephen. So kind of like Stephen was saying, this is a topic that is very sort of in vogue these days, right? I feel like at this point, if you aren't working on RL and human feedback, you're almost a minority in the machine learning department. But I think that oftentimes when a lot of this material is presented, it's presented in a way that is very sort of mechanical and doesn't really get at what I think is kind of going on under the hood and is what is the sort of more kind of underlying algorithmic perspective on this stuff. The reason I think that that sort of more kind of base theoretical perspective is important here is that this is a field in particular that is evolving very rapidly, right? Like every 2 to 3 days on Twitter, there's somebody who claims they've beat every other algorithm that's ever been released in this field. And I think when sort of learning about this sort of stuff, it's important to learn the sort of underlying principles that govern a lot of things, rather than focusing on whatever version is particularly popular on a particular day. So when presenting this stuff, there's kind of a good amount to cover. So I decided to split up the lectures between today and Thursday as follows. Today's mostly going to be about the setup. I'm going to try and give you a picture of the way I think about RLHF and just sort of, I think, the sort of cleanest sort of way to think about the way a lot of these algorithms actually boil down to things. And then on Thursday, we'll actually talk about sort of the punchline. We'll talk about why really do we actually need RL for this whole thing? Because I think it's actually a much more subtle and interesting question than I used to think it was. So before I get too much into things though, who is scribing for today? Cool. All right, good luck as always. And yeah, so let's dive into it. So today we're gonna talk about, primarily 3 questions. First, we're gonna talk about what the sort of fine-tuning problem is, what are we actually getting in this sort of language model fine-tuning kind of era? Well, what is it we're trying to do? And then we're going to talk about kind of 2 families of algorithms. The first will be sort of when people say RLHF, what they usually mean, which is a sort of 2-stage algorithm, where you first collect a bunch of data and fit a reward model on it, and then you use this reward model to basically give you labels for some sort of downstream reinforcement learning procedure. So this is sort of an older idea than it might seem. Fun fact, when I was an undergrad, I worked on this sort of stuff. Back then, it was much less popular than it is now. So it's been really weird watching something that you thought was this random thing you worked on as an undergrad get really, really popular since. But this is sort of what I would say is the more kind of classical pipeline for a lot of this stuff. And let's say 2 to 3 years ago, there is this sort of new flavor of algorithms for this problem, which I'll broadly call direct alignment algorithms. You should think of these as doing sort of a single-stage optimization, not first learning a word model. And the most famous of these algorithms is DPO, direct preference optimization. So we'll be talking a little bit about sort of what those algorithms are and kind of how they kind of fit into this overall picture. Today, we're not going to talk much about why you prefer one of these algorithms over the other. That's really what the sort of lecture on Thursday is going to be on. But today, I just want to give you a picture of what are the different things we could talk about in the first place, if that makes sense. Cool. Awesome. So let's dive into the first part, which is that, okay, how are we going to think about the fine-tuning problem in this course? And it's really going to be that it boils down to something that looks just like a regularized maximum likelihood estimation. So maximum likelihood estimation, increasing the likelihood of the data is something we've all hopefully seen before. The thing that's a little bit different here and why it's a fine-tuning problem rather than just a general optimization problem is that we're also going to want to stay close to some prior model in some sense that I will make more precise. Before we get too much into the math though, No, I think that it's important to kind of get a picture of why this is useful, why it's interesting. So I'm sure people have seen a lot of this stuff already if you played around with things like ChatGPT, but I thought I'd give you a few examples that I think are kind of cool. So if you spend sort of nearly the amount of time that I spend on Twitter, you'll often see memes that look like this. I don't really know what this is about, but at the highest level, it's something like this. The way language models are trained, right, is there's some sort of unsupervised pre-training procedure where basically you download all the text you can off the internet, and you basically say, okay, given some piece of text, predict the next sort of token, right? And this gives you a kind of a blobby looking guy, something like this. What this means is that you basically end up with this thing that can regurgitate random text on the internet, but isn't particularly useful for doing anything you'd want, right? Like, it's not as if you want your chatbot to just spit out random text on the internet, right? You want it to actually do something that's useful for you. So the sort of thing that RLHF does is, it puts a happy mask on this guy. What that means is that basically it kind of says that, okay, rather than doing this sort of unstructured random regurgitation of text, what it really does is it gives you some sort of more controlled behavior that is more aligned with the preferences people have for what they want their chatbots or whatnot to do. I think though that this sort of paradigm became popular at first because of language models, but it's expanded much more broadly and allows you to do very sort of like subtle things. So one example of this that is from some of Wen's work that I'm not sure if he'll be talking about this when he gives his guest lecture next Tuesday, but it's related, is that you can do this to, let's say, even tune something like a consistency model, which is basically a fancier diffusion model. So maybe you train on a bunch of internet data and you're able to get a model that can, generate somewhat realistic pictures of like cows or tigers or sheep or things like this, right? But then what you can do with the sort of like fine-tuning process you get from RLHF is you can ask it instead to do these sort of like more kind of subtle things, like generate me an aesthetically pleasing image of a cow, right? And the thing is that like, if I asked you to write down a reward function that said what aesthetically pleasingness is, it's a really, really hard thing to do, right? It's very hard to actually specify what we care about for these sorts of problems. So part of the challenge with this sort of fine tuning or getting it to be sort of aligned with people's preferences is that I need to essentially learn what people's preferences are from data in some sense. So just like we had talked about how in imitation, one of the reasons you want to use imitation learning methods, right, is that it's often very hard to write down this reward function that precisely captures what good behavior is, right? Like, for example, it's really hard to write down a function that captures what good driving is. The same thing is true for this sort of like RLHF setting, where it's very hard to write down this sort of model that really captures what sort of like an aesthetically pleasing image is, right? Like if I asked you to write down a function to optimize data from this to this, I have no idea how to do that. You can also, maybe the more canonical example of this is, actually go ahead.
Yeah. Can you go back to the previous slide, the Shoggoth?
Yeah.
So I think my understanding is the point that the Twitter community was trying to convey with this is that RLHF is something that we should be weary about because it does not actually align models, but rather just make the impression that models actually try to align with human preferences, while they actually might not. So this seems to be like trying to counter the idea of like, should we actually do RLHF?
Yeah, that's a deep question. It's a little bit above my pay grade. But I think what I'd say is that I do think this is sort of accurate in the sense that, we really don't have that much fine-tuning data, that, the happy mask is only this big, right? And oftentimes what you'll see is that when you're doing these sort of fine-tuning procedures, you can end up like hacking your reward model in some sense, right? Like if you throw enough compute at it, you'll start generating things that are pretty far from what you actually want. So that's part of the reason why I think that, this image is accurate. I don't know if I want to make a strong statement on whether you should or shouldn't do it, but I do think that like if you think of the relative size of the mask to the relative size of the guy as being, like the amount of data you're using for it, it might maybe becomes clear why a lot of sort of framing this as just a fine-tuning problem more than just a general optimization problem is important. That makes sense? Yeah. Good. Other questions? Yeah. Good to know someone else also spends too much time on Twitter. But, okay, so another example, this is maybe the more canonical example, is from the, the Instruct GPT paper, right? So I think this gives you another sort of like piece of visceral understanding what you get out of this, right? Like maybe when you do some sort of like thing where you train your model on all the text on GitHub, right? You get this thing that can tell you like quite literally, this is what each of the lines in this piece of code are doing, right? Like it's telling you, okay, I'm storing the value of C naught here, I'm literally writing this sort of thing, right? Versus here, right, when I actually fine-tune the model, I'm able to tell you that I'm actually like meaningfully what I'm doing here, right? That I'm actually computing this sort of binomial coefficient, right? And again, it's a sort of thing where like, okay, to go from saying this is good to saying this is good, it's really, really hard to write down a reward function that actually says this is actually what you want to do. And we're going to have to basically learn this reward function from data. So it should be very sort of ringing some bells, like what we talked about when we talked about inverse RL and things like that. Okay, so let's now make things, let's say, a little bit more formal. So the usual RLHF pipeline, which is not, in any sense, I think, fundamental, but the sort of way a lot of the models are built looks something like this. You kind of have this three-stage procedure. So first what you do is you kind of do this whole pre-training procedure, right? Where you basically do next token prediction on random stuff on the internet and you get this kind of blobby guy, right? Then what we want to do is instruction fine-tune it, which means that we want to be able to follow instruction and sort of do what we ask it. And it's sort of important for things like chatbots, right? Like if you ask your chatbot to do something, you want to be able to do that thing. So the way this looks is something like the following. You first do something that looks essentially like an imitation procedure. So this is usually called supervised fine-tuning, or SFT for short. But really under the hood, this is just imitation. So what you do is you basically, get some prompts of like questions you want to get answered. You ask basically a demonstrator to tell you, okay, how should I answer this question? What was a good answer to this, right? And then you basically use this to fine-tune the model. And the way this is done in practice usually just boils down to something like behavior cloning. I don't think there's anything particularly fundamental about using behavior cloning here, other than the fact that it is computationally simpler than a lot of other things. So once you have this model that can kind of basically spit out text that's like vaguely along what you want to do, usually you want to sort of fine-tune a bit more to be a bit more precise and give you what you need. So this is sort of a two-stage procedure usually. The first is going to be fitting a reward model, or an RM for short, which is really going to be training a classifier. So the way this looks is something like the following. You basically give the prompt to the model, and you ask it to sample like a set of completion. So you ask it to say, okay, what's one way you would explain this to a 6-year-old? What's another way you would explain this to a 6-year-old? Then you ask a real person, usually, okay, which of these do you like more than the others? So you get sort of a rating of this being better than that. And then what you can do is then use this basically as labels for classification problem. You're able to say that, okay, I prefer this to this, and now this is basically my label for a classifier where I want you to rank D over C. Then once you have this classifier, right, what you basically do is you do RL, where you basically use the output of the classifier as the score, right? So you basically use the logits of the classifier as the reward for a prompt and completion pair. And then you run whatever your sort of favorite policy gradient algorithm is and kind of see how things work out. One thing I should note here is that I don't think it matters as much as many people will tell you what policy gradient algorithm you use here, whether it's PPO, reinforce, or GRPO. I was going through all the project proposals over the weekend, and I was surprised by the number of people who mentioned GRPO. I really don't think there's anything special about it. All these things work around the same. I think we're just really hill climbing on a thing that doesn't matter too much. I will say my favorite of these algorithms is something called REVEL, R-E-V-E-L. When we'll be talking, in my very biased view, when we'll be talking about that on Tuesday. But you can really think about using whatever sort of variant you want here. And I think that really, if you do your hyperparameter tuning pretty well, things all seem to work roughly the same, and it really becomes a question of what is the easiest for you to implement, given the infrastructure you have. So this is the overall kind of pipeline here. One other thing I should note here is that usually, when in this whole preference fine-tuning procedure, which is sort of the last two stages here, maybe let me write that out explicitly. These last two stages are called PFT, or preference fine-tuning, is that we want to stay close to the model we actually got out of the imitation part here. So sort of for the rest of this talk, I'm going to use this notation of pi-ref, or a reference policy you want to stay close to. And you should really think of that as often being just the output of this sort of supervised fine-tuning procedure. It's a policy that does something pretty reasonable, and now we just want to essentially get a little bit more sort of careful fine-tuning. So I'm now going to talk a little bit about how we sort of formulate this problem as an MDP and how we solve it and things like that. But any questions about the sort of like highest level picture of things? Good. Okay. So let's think about how we formulate this problem as an MDP. So the way I sort of framed it, right, we're going to have some sort of prompt, some sort of question we give the model, and then we do some sort of autoregressive generation to basically give us a response, and then I'm going to call that a completion. And then once we have this completion, right, we then get some sort of score from a reward model for it. Let's dive into this a bit more. So we sort of talked about the components of an MDP, and all of them are kind of on this slide. I'm just going to try and add in the notation now. So first question, can anyone tell me, like in MDP notation, what a prompt is?
Initial state distribution.
Exactly, right? So our prompt is going to be some initial state. I'm going to call it S naught. Sample from some initial state distribution, let's call it rho naught, right? The next thing is, what about a token? When I'm picking a token, like a particular sort of, let's say for simplicity, like a word, right? Often in practice, it looks something more like byte pairs. But can anyone tell me what that is? Like what a token is in sort of our MDP formulation? Action, exactly, right? So we're going to say this token is going to be something like A1 in our action space A, right? And we can keep doing this up to some, let's say, maximum horizon big H. So when we're doing this sort of autoregressive generation, right, we're sort of looking at everything we've seen before, so both the prompt and the previous tokens. So this means our state often looks like basically, the previous state and then the next token. So, at this step here, it's going to basically be the initial prompt plus the first token we generated. Then you're going to get something that looks like, S naught, A1, A2. Then you're going to eventually get something that looks like SH equals S naught, A1 all the way to AH. So really just sort of concatenating all of these tokens together to get the overall thing, right? And this means we can really think of a completion as really just being a trajectory sampled from our policy, conditioned on some initial state. So, questions. First, given this picture, can anyone tell me what the dynamics here are? Good, but like more precisely. Like what are the probabilities? It's deterministic, so it's a 0-1 probability, but more specifically. Anyone?
You're starting at the next state is just wherever the previous state was plus the new token that you're in.
Yep, exactly, right? So we're going to say that like the transition dynamics of S prime conditioned on SA, I mean, it's a bit of a silly distribution, but it is a distribution. It's going to be 1 if S prime is going to be equal to S concatenated with A, and 0 otherwise. So, good. So, one thing that's cool here, like someone just mentioned, is that these are deterministic. There are a few other things that are kind of special about this set of dynamics. Any other thoughts?
You argue that it's maybe not dynamics, but it's your policy. Right? Like if you have a transformer predicting the next tokens autoregressively, then it's deterministic, but Is it still dynamics?
Yeah, that's a good question. So different people disagree about this, but the way I think about it at least, I think of your policy as picking the token. So it's the one that picks A conditioned on S. And the
Yeah.
dynamics are what tell you, given S and A, you get the S prime.
Oh, so you said the dynamics is the setup of your autoaggressive problem, basically.
Yeah.
And okay, that makes sense.
Right. So it's the prediction that's the
Yeah.
policy, it's the auto-regressive
Okay,
nature.
okay.
Yeah. Good question. Other questions?
Since you only get like reward in the end, can't you just treat our generation as just go after?
Yeah, so, good. So let's talk about this more. So first, right, is that we're gonna get a word at the end. So we're gonna really look at we just need to look at, let's say, S big H for that, right? The final state, because this final state actually includes everything we've seen so far, right? So sometimes people will kind of say that RLHF is a contextual bandit for this reason, that this is a one-step problem where your action space is just like picking H things at once. I think that, this is like literally true in the sense that you could think of this as a contextual bandit over solving an H-step problem, right? But I don't think you necessarily need to frame it that way, right? You can think about like, really what you're doing is you're picking a sequence of tokens. There is sort of like decision-making involved, right? And it turns out that, practically speaking, treating this sort of problem as a contextual bandit only works for relatively short horizon problems. So if I have to generate, let's say, I don't know, under 100 tokens, basically treating it as a contextual bandit seems to work fine in practice. But as you get to more complicated things, let's say you have like multi-turn dialogue with a person or something like that, then you actually want to do proper credit assignment and figure out like, okay, this was not good, that was not good, things like this. So as you sort of increase the horizon of the problem, or you add sort of a human in the loop, then the sort of contextual bandit thing breaks down a bit more. Make sense? Good. Other questions? Okay. So one thing that I think is kind of cool here is that, remember in the last lecture, I drew all these like trees, one thing that's kind of cool here, I think, is that these dynamics are tree structured. In the sense that basically I start from some state S naught, and I can play like A1, A2, A1, A1, A2, and then after playing A1 and A2, I can, play A1 or A2 here, same thing here, same thing here, right? Really what tree structured means is that from my state, like at any of the leaf nodes, what I can do is I can back out the entire sequence of actions it took me to get to a state, right? So this means that sort of state space grows exponentially with the horizon because I'm not like losing any information as I sort of go along. So we kind of had gone to this tree structured problem as an example, sort of like a worst case problem for exploration in RL, but turns out in language we are precisely trying to solve this worst case problem. There's one other thing that I think is kind of interesting here. So last lecture we talked a lot about doing resets in RL, right? Like generating from an expert state, seeing what happens and stuff like this, right? Can anyone tell me what a reset is for language? Let's say I gave you some partial, piece of text that, let's say one of the supervised fine-tuning labelers had given you, like the first 10 tokens they generate. And I told you to, complete the rest of the episode, right? What is that actually doing? It's just that, I think it's actually really cool. It's that a reset is just generating from a prefix. We talked about how for problems in robotics, right? Sometimes it's really hard to just like reset to a particular state because you can't, just like stick your humanoid halfway through a backflip, right? But for language, it's actually extremely easy. It's just completing a prefix, right? So this makes a lot of sort of things when it comes to optimization and kind of exploration much easier. When we'll talk about this in greater detail in this lecture, I think, but yeah.
What is your definition of a prefix?
So think about,
Just cut it off somewhere and.
yeah, right. So think about something like, rather than just the prompt, right? I said, okay, I had this question, and then I gave you the first, 10 words of what the person said, and I said, okay, now finish the rest of the prompt the way they would have, right?
Okay.
You can really think of it just like appending to the prompt in some sense, and that's really what a reset, what a generating from a prefix is. But this makes exploration a lot easier, which is quite nice. Cool. So any other questions about the sort of overall framing of this in MDP?
So why can't we assume that logarithmic is based on range because the sentence, the end token, the tokens after the end token is meaningless?
Yeah, that's a really good question. So for simplicity, I'm just using just a fixed horizon h here. Usually what happens though is you basically think of having your policy being able to generate like an end of sentence or an end of generation token. And after that, you have a special case in the dynamics where basically you just repeat the end of sentence token over and over again. Then when you're actually like implementing policy updates and stuff, you basically have a filter so you basically don't take any gradients through these extra tokens because they're like you said, meaningless. But usually you have some sort of like max generation length, just so you don't like run out of memory like during policy optimization. That's a good question. Any other questions? Cool. Okay. So maybe just to recap those points, I think there's a couple things that make this language MDP special. One is that the dynamics are deterministic, they are known, and they are tree structured, right? This means a lot of this is both good and bad. Deterministic is nice, we talked about for a few reasons. Tree structured is less nice because you don't have this sort of exponential blow up in the state space size. The fact that the dynamics are deterministic and known though is nice in the sense that I can just do easy resets. They're just generating from a prefix, right? I don't have to figure out how to, get my robot do this complicated thing in simulation, then worry about the sim to real transfer aspect of things. And then the last point, which I'm brought up, is that really I think that's interesting here is that the word function is non-Markovian, right? It's not like I tell you when I'm evaluating a sentence how good each word is and I sum up those scores to tell you how good a sentence is, right? I need to look at the whole thing holistically at once to tell you how good that is. So unlike the sort of Markovian decompositions we talked about earlier, here you have to only get the sort of feedback at the end. This doesn't necessarily mean you should treat it as a contextual bandit, but it is different than what you talked about earlier, than there is a sort of like clear token-wise decomposition. Does that make sense? So this is how we frame it as an MDP. Right? Now let's think a little about how we actually do learning in this problem. So I'm going to think about the particular version of stuff here called preference fine-tuning. So kind of just to bring in a little bit more notation, right? We're going to sample multiple completions from our policy. Let's call them psi1 and psi2 here. Then we're going to get essentially ask a person which of these two completions to this prompt did they prefer. And as you can tell from this like little thinking wheel, they're thinking very hard about it. So we're going to get some sort of label that looks like, okay, we prefer psi1 to psi2. This sort of like squiggly greater than is how people write prefer to. So, let's say they liked the first completion more than the second completion. I'm going to just draw that out here as boxing this in green and, saying that this preferred completion here, I want to box it in red. Then what we can do is we can sort of collect a data set of all this stuff, right? Basically it looks like this. We're going to have some data sets D, which is going to look like basically initial states, a preferred completion, and a dispreferred completion. I'm going to use psi plus and psi minus to refer to the preferred and dispreferred completions. So basically, you should think of these as trajectories that share an initial state. And we know that, people prefer one. So, I think a good question to ask at this point is like, why are we actually doing learning from preferences here rather than just collecting extra demonstrations? I think there's both pros and cons to it. Can anyone tell me why someone might prefer actually getting preference data rather than demonstration data, or the other way around? Yeah.
I mean, it's like providing an explicit reward function versus having the model infer some latent reward function, like from demonstrations. It might get preference, but it would be less, like I suppose, sample efficient. But if you give it preference data, it's much easier for it to understand what the human incentivizes or rewards, essentially.
Yeah, so I guess we're going to still need to infer a word function here, right? Like we're still going to need to infer one from this preference data, right? So there still is a need to do that. I do agree that maybe you can get more nuanced comparisons, but there is still a need to do a reward inference problem. Yeah.
Is it maybe that the state distribution is in the distribution of your model?
Good. So another thing that is kind of nice here is we're getting sort of on policy feedback, right? Like I'm actually sampling from my model and saying, okay, like, how would you sort of, which of these do you prefer, right? But this isn't fundamental to preferences, right? Like for something like Dagger, what I could do is I could ask human, right, to complete the prompt after like the model finished the first like 10 tokens, right? I could do the reverse of what we talked about earlier. Yeah.
The collection perspective is a lot harder to collect demonstrations where the people might be considered really good compared to the model and stuff.
Yep. I think that's actually primarily what this boils down to. It's just easier to ask people for preferences, right? Like you don't have to have someone type a really long like thing, right? You don't have to have some expert like tell you how you solve, an IMO problem. You just look at the two things and say which one is better, right? So I think it just really, in practice, boils down to easier data collection. There's a downside to this though, for collecting preferences rather than demonstrations. This one's a little bit subtle, but does anyone have any guesses for why?
I think if ChatGPT asks this question pretty often, usually both are almost similarly good. And I guess it's hard to say how much better one is over the other. So you get a really harsh reward for a really small or arbitrary difference.
Yeah, that's a good one. So like, right, like think about getting two things where these two completions only differ by one token, right? And it's like, well, am I really gonna get useful feedback there? Unclear. So in practice, you have to be a bit careful about this, but usually what you do is, there's some sort of like sampling temperature when you're sampling from your policy. You essentially raise the sampling temperature so you get more random generations when you're collecting human feedback than when you're actually like deploying the final model. So agreed it's a thing, but I don't know if it's fundamental to preferences. Yep.
You'll only have pairwise comparisons between all your data, all your completions. Yep. You won't know how to deal with the completions, or even if you have partial data for true ordering.
Right. But the same thing is true for imitation, right? Like, I don't know something I didn't see in the demonstrations how good or bad it is, right? Yep.
If you have multiple preference options, there could be the case of those preferences being intransitive. And so that's also a problem, right?
Yes, good. I am going to talk a lot more about that like 3 lectures down the line. But yes, so the idea there is that like, it might not necessarily be true that I can order all completions to a prompt, right? It might be true that like, maybe even a single rater can't like sort of tell you how much you refer every single completion to a prompt to every other one. It gets more subtle though, I think, in practice, because oftentimes you're aggregating data when you're collecting it, right? And really, what a lot of these models are essentially assuming under the hood is that the majority of your raters think a single completion to a prompt is preferable to all other completions to a prompt, right? Which if you ever look at any of these data sets is like completely false, right? Like people can barely agree on one prompt being better than another. The sort of global ordering, the sort of transitivity is much harder to get. But it's a good point. There's one answer I'm still looking for though. It's much simpler.
Could be just that different people have different preferences.
Yes. So different people have different preferences, and you have to worry about sort of reconciling them. That was sort of the related to the point we were making about like transitivity and preference aggregation. The last one is that you really only get like one bit of information, I would say, right? Like when I give you a demonstration, right, I give you this whole thing, and I said, okay, this was like a good thing for you to do, right? When I get preference data, right, I'm really only telling you that this was worse than that, right? I'm not telling you that this was a good thing to do or that was a bad thing to do. I'm only giving you like one bit of information. So it's easier to collect the data, right? But you also get much less for each query than a demonstration, right? So I remember when like RLHF was kind of getting more popular, right? I feel like there were a lot of people who had very strong opinions about SFT versus preference fine tuning. I think it's much more subtle than, like, there's factors in either direction. Cool. So now, given all this data, right, we have this data set of prompts and pairs of completions with a sort of each one is referred to another. We now have to think about how we actually learn from this data, right? So in preference fine tuning, really what I'm going to say our goal is that we're going to maximize the relative likelihood of preferred to dispreferred completions to a prompt, right? This is the only data we have, right? This is the only thing we can do here. So before we talk about the math, let's just think about the higher level intuitive thing we're trying to go for here. Why can I not just maximize the likelihood of the preferred completions? Why do I need to maximize the relative likelihood? Someone had already kind of said this, but I'm looking for someone to say it again, if possible.
Like if both of them are kind of bad, then like you don't want to have it just learn like the slightly like less bad one, but you want it to learn like what makes one worse than the other.
Exactly, right? Like, what if I have a pretty bad base model and I sample two trajectories from it, two completions, and they're both terrible, right? Like, why would I want to increase the likelihood of both of them, right? That would just not, or even the better one, right? All I want to do is just say, no, I want to separate them. I don't want to make one, necessarily more popular. So the relative part here really matters, I think. So this equation probably doesn't make a large amount of sense the way I've written it. I'm going to make it more formal in a bit, but just intuitively, you should think of part of what we're trying to do in preference fine tuning is maximizing the likelihood of the data or minimizing the KL divergence to your data set. And this data set is, contains both the positive and the negative samples for each initial state. Okay. So the next thing I want to think about is this sort of this prior regularization. This guy right here. So maybe one thing I'll note here is that here I'm doing some sort of forward KL thing here, and here I'm doing reverse KL, right? Like forward KL because the policy is the second argument to the KL thing. This is sort of an off policy thing. Reverse KL here is an on policy thing where the policy is the first argument. So before we even get to the details of on policy versus off policy stuff, why do I need this regularization? Why does this matter?
If you don't have it, then you're basically ignoring retraining.
Yep. Exactly. Now here's a somewhat harder question. Let's say for this data set, I had a crazy amount of money. And what I did was for every prompt in my data set, I asked people to compare literally every possible completion that a model could generate, like every one of the exponentially many things, right? So I had this data set here have like full coverage. If you remember what Yuta was talking about, I see every pair of completions to a prompt, and I give you a label of which one I prefer to the other one. Would I still need prior regularization then?
Is this coverage in S02? Or is it just a rollouts from whatever S0 you sample?
Good. So let's say there's just some set of S0s I can care about, right? Some set of prompts. Let's say for every one of those prompts, I get full coverage over every pair of completions. So it's like
Okay.
full coverage in that sense, yeah.
Yeah, I feel like you've just created a new training data set similar to the prior.
Yeah, right? Like, if I actually told you what every pair of completions the ordering was, right? Like, why do I need to stay close to the prior then, right? Because then I've actually gotten human feedback on every single thing, right? So really the reason you need this prior representation is because of this sort of limited coverage here, right? Because if like I actually told you what people preferred for every possible completion to every single prompt, right? That would just be fine. I would just maximize that likelihood. There's no need to stay close to the prior then. So there's really a sort of interplay here between the lack of coverage here and the need to stay close to the prior. So that's sort of the overall objective. We're going to talk about algorithms now, but hopefully that high level picture makes sense. So what we're going to talk about next is the sort of like the two-stage RLHF process. What is it actually doing? It's basically going to look like doing something like maximum likelihood estimation over word models, followed by doing something that looks like maximum entropy RL or soft RL over policies. So I'm going to kind of introduce two pieces of notation now. The first is going to be an assumption, and the second is going to be just like a reality, right? So the thing that's the reality is that in my data set D, right, with some probability, my raters prefer some trajectory psi1 to some trajectory psi2. For simplicity, just assume we see all complete, all pairs and labels here. Don't worry about coverage for this particular point. So this is sort of ground truth, how often raters prefer some completion psi1 to some completion psi2 in my data set. The assumption we're going to make, just for simplicity for this lecture, is we're going to assume something called Bradley-Terry-Mahler preferences, which says that, okay, given some reward model R, the probability of preferring psi1 to psi2, conditioned on some initial state, is basically going to be the sigmoid of the difference in rewards between these two trajectories. This is an assumption, right? And like we had just talked about, right? This is sort of assuming transitivity, by which I mean you can order all completions to a prompt in a way that kind of like actually is like, you know, a total order over things you could do. Or equivalently, sort of assuming all raters mostly agree. So this is not really a reasonable assumption in practice. We'll talk about how to relax it in a later lecture, but for simplicity, let's assume it for today. So given this sort of picture, right? Let's think about this sort of two-stage procedure. The first stage, fitting a word model, I'm going to now argue is basically just maximum likelihood estimation, fitting a classifier, right? So I'm going to put this all up at once, then we can talk it through. But so first thing we're going to do is we're going to say, okay, over reward models in my reward class big R, I'm going to try and minimize the KL divergence between my ground truth empirical distribution under my data set and the sort of probability preferring one trajectory to another, my model sort of like spits out. So again, this term right here is some sort of like forward KL. Then what I'm going to do is I'm going to end up with this thing that is just maximizing the log of the data, and it's sort of like dropping a term. So a bit more explicitly, right? Let me go from here to here, right? we have some like DKL from some distribution P to some distribution Q, right? This is just the expectation under P of like log P minus the expectation under P of log Q, right? This is sort of just the definition of KL divergence, right? And then if I'm optimizing the second argument here, Q, right? The first term, the entropy of P doesn't actually affect the optimization process, right? So I can sort of just drop that there, and then I change the minus to a plus. That's why the min goes to a max, and you end up with this sort of thing here. So this is just saying that maximum likely estimation, same as minimizing the KL divergence to your data set. Then what we need to do is be able to say like, okay, what is the, probabilistically speaking, what does a reward model tell us? How often, some trajectory psi plus referred to some other trajectory psi minus. That's where we sort of bring in this Bradley-Terry assumption. And that gives us this sort of like final sort of objective here, right? All of this though is just really a more formal way of just writing something you've hopefully seen before, which is just logistic regression or training a classifier, right? All we're doing here is training a classifier that says, okay, I want you to classify which of these two trajectories was preferred, right? And we want to say psi plus is referred to psi minus, so I'm going to maximize the difference in rewards between them. Does this make sense? Any questions about this? Good. So, we're going to sort of build up this picture over the next few slides, but you should really think of there being some space of word models, R, and we're going to have some R hat we get from maximum likelihood estimation. And really you can think of reward modeling as doing a projection onto the space of reward models under this sort of forward KL metric. So really what we're saying is saying, okay, take my data set, pick me a word model that sort of, maximizes the likelihood of the data. Okay, any questions about that? Hopefully this is something people have seen before, that, minimizing KL is the same as maximizing likelihood. Okay, so now let's get to another thing we hopefully remember, which is the sort of like soft RL and pre-regularized RL kind of stuff. So given some reward model we got from, let's say, RLHF, the sort of fine-tuning RL problem usually looks like something like this. I say, okay, I'm going to sample some trajectories from my policy pipe. I'm going to plug them into my reward model. I want to try and maximize that probability. But I want to stay close in terms of this sort of reverse KL thing to the reference policy, IRF. I don't want to go too far because this reward model was only fit on a data set with limited coverage. I don't trust it kind of out of distribution. This is what people mean when they talk about like word model over-optimization or reward hacking or things like this. It all kind of boils down to this limited data set coverage. So we sort of talked about this last time about how you can really think of just expanding this KL term into an expectation over trajectories drawn from pi as well. And you get a term that looks like this, right? That this whole term here is really just this term right here. And then we'd also talked last time about, or a few times ago, right, about how what you can do then is really think of this sort of entry regularization or this KL regularization as basically just adding a term to your word function, right? So rather than just getting the R hat from the MLE, you basically add a penalty based on the log ratio between what your policy does and what the reference policy does. So all I'm doing here is I'm expanding out the definition of KL, and I'm noting that both of these are expectations over trajectories drawn from my policy, so I can kind of stick this and this together and get some sort of like composite reward, that is the reward output by the word model, plus this KL penalty for straying too far from the prior. So whenever people end up, so you basically end up adding these two guys. So whenever people actually implement this stuff in practice, it often boils down to something that looks like, basically take whatever your favorite policy gradient is, get a word model to score a completion to a prompt, to add in this sort of KL term. This gives you some sort of composite reward, and then take a policy gradient step on this sort of like reward plus this extra. Does that make sense? My point here is that like this sort of KL regularization thing, given we're already sampling from our policy, it's actually not too hard to implement. It's just augmenting the word function with these extra terms. Okay, cool. So we'd also talked a few times ago about that there's sort of a closed form solution to this sort of problem, right? Does anybody remember what that closed form solution looks like? It's the same solution to sort of like the maximum entropy kind of problems as well. If you're confused about KL versus entropy, you can even just pretend it's entropy for a second. This was both what I think Drew talked about when he gave his lecture, and also what we talked about when we were going through the max IRL derivation a while back. You guys definitely know this one.
Something exponential.
Yes, there is an exponential. Good. So I guess I'll give it to you. We said that something like the following: the probability of a trajectory, the optimal soft RL policy, so the thing we get here, conditioned on some initial state, is basically kind of the softmax over word values, right? And I'm not going to go through the derivation more carefully, but basically when you do this with a KL thing instead of a entropy regularization, you basically end up multiplying the prior in. That's what it just boils down to. So, okay, so this part right here is something we've seen before, right? Where we just say, okay, the trajectory distribution is really just a softmax over word values. That's how often I want to play a particular trajectory. The part that is maybe a bit special to the RLHF setting is this equivalence here, right? Or I can just write out the trajectory probability just in terms of a product of per token policy probabilities. Can anyone tell me what sort of assumption I'm making here so I can do this? Like what factor can I drop and why can I drop it? Yes, right. So normally when I want to give you a trajectory, the probability of a trajectory, right? I also have to factor in the dynamics, right? I tell you, okay, when I take action A in state S, this is my probability of ending in state S prime, right? But here we talked about, like, assuming this is a valid trajectory, all those probabilities are 1, right? So this is just like also multiplied by 1 to the h, which is just still 1. So that allows you to sort of write this out a little bit more explicitly. So I don't think I'm gonna have time to go through this more carefully today, but just trust me when I say this, that really the sort of soft RL stuff can be interpreted as a reverse KL projection from the space of word models to the space of policies. So really, you can really think of this as end-to-end, as basically doing a projection under via maximum likelihood estimation onto the space of word models, and then going from the space of word models to the space of policies via this sort of reverse KL projection. So I think when you see it written out this way, there should be a kind of natural question in your head, which is why am I taking a detour through reward models if at the end of the day, all I care about is a policy, right? Like, why am I doing these two projections? I could also just do a forward KL projection onto the space of policies, right? That seems so much cleaner, much simpler, much more direct. We're going to talk about what that looks like in a second, but it turns out there is a good reason to not do that, but it's kind of subtle, and we will talk about how you do that today and why you shouldn't do that next lecture.
Is a direct projection basically supervised fine-tuning?
Right, so it could be something like, I mean, here, right, we think of the data set here as being preferences, so it's gonna look something more like DPO or direct preference optimization. But yeah, it looks pretty close to like some sort of offline maximum likelihood estimation procedure, yeah.
Can you explain to me by KL projection?
Yeah, sure. So we talked about how maximizing likelihood, right, is basically the same thing as minimizing the forward KL, right? So we can really think of this as like, okay, find me the reward model in my reward model class. That's sort of the closest to whatever generated the data under this sort of forward KL metric. Does that make sense?
Yeah, so you're using the word projection to mean basically finding the optimal thing.
Right, right. It's saying like, okay, I'm gonna give you some distance metric between my data and whatever I'm choosing, and pick the thing that minimizes that distance metric, which is what a projection is, right? Good. Other questions? Cool. So I'm gonna skip a page of math or two here. And let's talk a little bit about DPO. Basically, algorithms that look like DPO are going to directly maximize likelihood, aka directly do a forward KL projection over the space of policies without ever passing through the set of reward models, right? And I want to, again, emphasize how reasonable of an idea this seems, right? Like, at the end of the day, I just want a policy, right? So I think you have to be very particular about why you want to go through this detour of actually going through a reward model, right? The other reason directly maximizing likelihood over policies is really nice is that this sort of software L, this reverse KL projection step, right? That requires actually doing reinforcement learning, which is this huge, really computationally intensive thing, right? We are kind of literally solving the worst case tree structure dynamics problem, right? So if I can tell you I can do this via just pure offline maximum likelihood estimation, just supervised learning, that is really, really nice. So turns out there is a way to do this. And let's go through this. So basically what we're going to do is a certain kind of reparameterization trick. I have no idea if I spelled this correctly, so whoever's scribing, check that. So I'm going to just use this to denote the partition function, right? The sort of the sum of the exps, the thing that's in the denominator. And this partition function is going to depend on the initial state. The reason being is that I don't get to pick the initial state. That's sampled from some distribution, right? But I wanted to say is condition on some initial state, condition on some prompt. I want to have as much entropy as possible. And this is basically me writing out the probability of generating a trajectory under pi ref as just the product of the per token probabilities, right? Which we can do because the dynamics are deterministic. So the optimal policy looks something like this. It basically says, okay, the product of the policy probabilities, aka how often it'll generate a particular trajectory, is going to be equal to how often the reference policy would do it, times basically the exponent of the reward. So given this equation here, now what I'm going to do is basically take the log of both sides of this equation. That's going to give me this guy here. So all I'm doing is taking a log. Okay, this makes sense. Basically, I'm going to take a log of a product. I'm going to break it up into the sum of the logs. There's also a product here, and I'm going to be able to just add in the RSI there. And then log of a ratio is going to be the difference of the two things, so I'm going to get minus logs. Then given this guy here, what I'm then going to do is solve this equation for R. So I have this equation here. Here I've written pi in terms of R. I'm going to now solve for R in terms of pi. So that is just rearranging, right? I'm going to just add over the log, subtract over the pi ref. And that's going to give me this guy right here. And somewhat suggestively, just like we have I sub R there to denote the soft optimal policy under reward model R, I'm going to use R sub pi to denote, given some pi, the value of this expression here. So why is this interesting? Like why does this rearrangement matter, right? So when we talked about max IRL, right? We talked about given some reward model R, what I can do is I can give you pi star of R via this sort of soft value iteration procedure, right? Generally, you throw RL at it with an entropy regularizer, right? You use your favorite policy gradient. What we're pointing out here is I can do the reverse, right? Given a policy that is soft optimal, I can tell you what reward model would make that policy soft optimal. I'm doing the reverse direction of inference. So really what DPO is doing is kind of reversing the sort of accent things, inverting the equations. So fairly explicitly, we can express the reward model that makes the policy soft optimal in terms of the policy by kind of inverting the Maxent IRL equations, right? So when we talked about all these sort of Maxent things, right? It's like, okay, I gave you a reward, and I tell you, okay, the soft optimal policy has this sort of X bar kind of distribution, right? Now what I can tell you is I can tell you if I give you a policy, I can back out the reward model that would make it, I can back out the reward model and make it soft optimal, which basically looks at the logits of the policy. Does that make sense? Is that confusing? I haven't told you why this matters or this is the thing you should care about yet, but it's the fact that I can do this isomorphism in the other direction. Make sense? Cool. So I think the sort of subtle question one might have is, why should I care about this, right? Like why does this fact matter? Why does it matter that I can do this sort of thing in the reverse direction? The magic sort of happens when you think about, for some R pi, what the soft optimal policy is for the reward function R sub pi. So let's consider the soft optimal policy for some R sub pi, right? Now I'm going to just use this to denote proportional. I'm going to drop the z for a second, but that's going to be proportional to the exponent of the reward, right? We said for any soft RL problem, it's proportional to the exponent of the reward, right? What is this reward, right? We can just sort of expand it out, right? I'm also just dropping the reference policy for this because it's a little bit cleaner without it. The same thing holds true more generally, but I'm just going to plug in this guy right here. Now here's maybe a somewhat harder question. I can drop this log z, it turns out. Can anyone tell me why?
Initial state distribution is C, like, because it was like the set of S naught, right? So I think that
Yes, the initial
it's like
state.
a normalizing constant, sort of.
Right. So initial state distribution is so the initial state distribution is the same, but the second point you're making is what I was looking for, where like this normalizing constant is the same no matter what trajectory you pick, right? And if you have a softmax, right, and if you add 10 to all the logits, you get the same distribution out, right? You have this sort of extra degree of freedom for a softmax. So it turns out that because I'm adding log z to basically everything, I can basically drop it from the equation. And what this means sort of then, right, is I get this sort of thing here. And then I can basically, just rearrange these terms. And I just get this policy here, right? So the thing that's sort of magical here is that the soft optimal policy for R pi is pi, right? And this means that I can just optimize over R pi. I can just optimize over reward models, and then I get the optimal policy for free. Does that make sense? This is a kind of subtle point. basically what I'm saying here is, okay, let's pretend this this RPi thing here, right, was a real structure level word model. It is. It's a sum of these sort of like per token logics. What I can do is I can basically plug in what the form of that is and actually get out the policy here. And that's what this point here is, right? The soft optimal policy for RPi is pi. And the reason I think this matters then, right, is that all I then need to do is optimize over RPi, and I get the soft optimal policy for free without doing any RL. Right? Because I've told you that, okay, if I fit the right RPi, if I fit the right reward model, I just know what the optimal policy is. It's the pi that is here, right? And I don't need to do RL to actually compute it. So really, what I think another way of thinking about the sort of DPO thing here is, right, is that this is just saying that you can basically just do logistic regression when you like invert this equation. I'm going to put it together in terms of like the actual like algorithm in a second. But does that high level intuition make at least some sense? It's okay if it doesn't. Any questions about that? So at the highest level, right, what we're doing is we're pointing out that when we talked about things like soft value iteration, max anti-RL, I gave you a word model and I spat out the soft optimal policy. I'm now noting that I can do this thing in the reverse direction. When I give you the soft optimal policy, I can ask you to tell me what reward model would have made it optimal. And that is what this sort of R sub pi thing is. Then the point I just made is that, well, then I can actually tell you that, okay, if it follows this very particular form, I can just read off the optimal policy without doing an explicit RL step. So to kind of put it all together, what we end up being able to do is we can basically proceed directly by doing maximum likelihood estimation. We can proceed by doing maximum likelihood estimation directly over policies. So I'm going to bring back our Bradley-Terry equation, right? But now rather than taking an argmax over reward models for logistic regression, I'm instead going to take an argmax over policies pi. And then I'm going to basically use this sort of R pi score as the thing I'm trying to maximize the difference of. And then I'm just going to plug in what I had for R pi. And this sort of gives you the sort of DPO loss function you may have seen before, where you basically get this sort of log sigmoid from here, log sigmoid, and then you get this log pi ratio here. So there's one thing that's kind of subtle here. When I defined R pi, I had a partition function there. I had like a z of s naught, right? There's no partition function here. Why can I drop the partition function? If I have two trajectories that start from the same initial states, both of them are going to have the same partition function, right? S naught is the same. So basically the two z of s naughts cancel. And that gives you this guy here. So end to end, I think really what's happening here is you get a single step maximum likelihood estimation directly over policies. So I'm going to complete the picture for a second, and then we can talk a little bit more about any questions people have. So really we can think about things like DPO and the variance thereof as basically being a forward KL projection directly onto the space of policies. And, you know, under the hood, what we're doing is we're using this sort of kind of duality between these two things, right? Like when we want to go from words to policies, right? We talked about how there's basically this, this sort of like, this sort of soft value iteration thing. Sort of like hedge at every state kind of thing, right? And the DPO point is really that the isomorphism, you know, goes both ways. It also holds in the other direction. And this basically looks just like logistic regression. So yeah, I think in my head, the way I think about RLHF is really that it's doing this sort of sequence of two projections. And I think of the offline, people sometimes call them direct alignment algorithms, as just kind of skipping this extra detour to the reward model and directly optimizing off the policies. So I'm sort of like begging the question when I present it this way, in the sense that like, from this picture, it does not appear like there's any value in actually going through a reward model, right? Like I'm introducing an extra step into what could be a one-stage procedure. And I'm going to talk next time about why this is actually a good idea, but questions about the picture, yeah.
So shouldn't IMLE and IRHF be the same point?
Yeah, that's a really good question. So, not necessarily, right? So there are multiple reasons why this can be true. We're going to talk about what I think the main reason they wouldn't be true, or both. There's two reasons, we'll talk about both of them next time, but I think you're asking exactly the right question, right? Like the interesting question to think about, you should think about it before next lecture, is when do these two dots do the same thing, right? Like when is this extra step completely meaningless, right? And the reason this matters, right, is if I can eliminate this extra step, I can get rid of RL, which makes everyone's life much easier in terms of actually implementing things, right? Do you have any intuition for why they might be different? It's very subtle. Yeah,
Like,
very.
can you do a reverse like projection to R from pi MLE?
That's a good question. I guess it'd be kind of hard because I need to be able to tell you, I need to be able to give you the trajectory distribution for an arbitrary reward model. Right? I need to be able to sample from like X of R, which is a hard thing to do. That's a good question though. Yeah. Other questions?
I wanted to make sure I get this right. So the forward KL towards the pi is what DPO does, but is the forward KL towards the two-step, the forward KL and the reverse KL, is that what PPO does?
Yeah. So I would argue that something like PPO is really doing this reverse KL projection, this sort of soft RL entry regularized thing. I would argue that reward modeling, actually fitting the reward model in the first place, is what this sort of forward KL projection on the space of rewards is.
Oh, I see.
So I guess I'm thinking about like, okay, right, like if somebody just gives you a word model, great, you can use it for things, right? But given we can't write these down, right, we have to fit them from some kind of data, right? So the question is, okay, if I think of that sort of abstract data set object, what is actually happening with it, right? And so I'm basically compressing it to a word model, and then I'm turning it into a policy.
Because the two-step thing is what people usually call our proper RLG.
Right, I see.
Right, yeah, so like end to end, I would call this sort of, I'm not sure if I can draw this in a way that looks nice, but basically, maybe I can. If I grab this guy here, yeah, that
Can't pulse.
yeah, sorry. But this sort of two-step thing, right? Or maybe I can do it via highlights, maybe that works better, yeah. This sort of like two-step thing here, like both parts here, is what people usually mean by RLHF, like Stephen was saying. Yeah. Good question. Other questions? So I guess maybe the thing to think about before next time on your own would be the following. First, I made one really strong assumption when I was doing the DPO derivation. I'm not going to tell you what it is, but you should think about what I did, right? There's one assumption I made that is kind of ridiculous. And we will talk about what happens when that assumption is broken next time. It turns out, though, that even assuming this ridiculous assumption, there still is a reason these two things should actually be different. And that is what I think the sort of more subtle and more enduring answer to this question is. And that's what the paper Stephen was talking about at the beginning of lecture was on. That is my favorite thing I've worked on in my PhD, and we'll talk about that on Thursday. Maybe the other thing I'd like to note here, just to kind of get your mind thinking about this stuff, right, is the following. Kind of look at the similarity between the sort of preference fine-tuning picture I've drawn here and what we talked about for imitation, right? Directly maximizing likelihood over policies for imitation is just behavior cloning, right? You have a trajectory, you say maximize that likelihood, right? So you should really think of DPO and behavior cloning as being essentially analogous to each other. That DPO is basically preference-based behavior cloning. Then the sort of analog to RLHF is the sort of inverse RL procedures we talked about earlier, where I'm actually learning a word model from data and then using that for an RL procedure. So in RLHF, right, I'm learning a word model between preferred and dispreferred completions, while in inverse RL, I'm learning a classifier between what the expert did and what the learner did. So again, the word update looks like training a classifier, and the policy kind of looks like the policy update looks like doing RL with the learned word model as your word function. There's a lot of similarities here. The other reason I think it's interesting to think about in this sort of like vague information geometric perspective, right, is that there's nothing particular to preferences here, right? Like preferences actually don't show up anywhere in what I'm doing. So the arguments we're going to go through next time also apply for imitation as well, more generally. But I think there's sort of a general, more kind of underlying phenomenon here that sort of underlies a lot of things. Yeah. I think maybe the last sort of leading question I'll leave you guys with is, when we had talked about the value of interaction in imitation, right? We'd said it essentially boils down to being able to tell what mistakes matter from what mistakes don't, right? It boils down to being able to recover from the mistakes your policy makes, right? Think carefully about whether recovery is possible in language. It's a subtle question, and we'll get to it more next time. So yeah, like I said, this lecture is really kind of more the setup of a bunch of things, and then next time will be more the payoff of trying to explain how all these things come together. But yeah, thank you for your time.